This is StarTalk. I'm your host, Neil deGrasse Tyson, your personal astrophysicist, and I got my co-host, Chuck. Nice, Chuck, baby.
Hey, what's happening, Neil?
All right. I bet you don't know what we're going to do today. This is a new thing we're doing today.
Uh-oh.
This is going to be a stuff you thought you knew, like a second installment of that.
Right.
We did this once before, and it really caught on, and people wanted a little more of that kind of action.
It's because people want to know.
They want to know.
They want to know more and more.
They want to know new stuff, plus if the old stuff they knew was wrong, they want to fix it. Usually, most of the time. So, right off the top, just so you know, I'm going to talk about the metric system in the United States. Then I'm going to talk about the difference between speed and acceleration. Then I'm going to talk about heat shields of re-entering spacecraft.
Interesting.
Okay, it's an odd sort of collection there, but you'll feel it, I think, as we move through it. All right. So let's start right out. Are you old enough to remember when Jimmy Carter said we're going metric in the This is the early 1970s. Do you remember this?
I do not.
There was a whole commission to convert the United States to the metric system.
Yes. Well, good to know that worked out so well. As I drink from my 16-ounce glass. So good to know.
So good to know. So I joke about this because back then and today, drug dealers have always been metric.
Right.
Just think about that. They don't sell cocaine in pounds. That's in kilos.
That's right.
So
that'll get you the same. That'll get you another measurement of time.
One that Einstein hadn't explored yet.
That's right. Yes, exactly.
So I've heard people joke that if we had put drug lords as head of the metric commission in the United States, we all would have been metric within months.
Right. Wait, are you talking that afternoon? That afternoon, we'd have been 100% metric and high.
So what I want to try to communicate is that we're not as bad as it may seem. We are much farther along than we even admit to ourselves in this conversion. I just want to sort of put it out there, okay? And I'm going to tell you why. Because I don't want you to feel bad about this. Now, I, as a scientist, we're metric from the beginning. Right. That's not even a thing. Engineers are a little later in the listing, but scientists, we speak internationally, and that's the international system that gets used. Okay.
Right.
So, in fact, it's called Système International, the SI system of units. The meter, the kilogram, the second is in there, but everybody uses the second. So the French came up with the metric system. Did you know this?
No wonder we don't use it.
Where you get this editorial commentary? So it got implemented in 1789. And what was happening then in France?
1789.
Yeah.
89.
In part inspired by what happened in the United States.
Was that the Bastille storming and all that good stuff?
The French Revolution, yeah.
Right.
Yeah. So part of that sort of overthrowing of all previous order, that was the occasion. If you're going to do it, that's a good time to do it.
Right.
In addition to the rolling heads, you throw in the metric system.
We need a way to figure out how these heads roll, Father. How is it that we get the head to roll, Father? Do not put the basket down. Let it roll, and we shall measure in a new way. I see the head go from the guillotine all the way down. As I smoke a cigarette and watch.
That's exactly how it happened.
Yes.
All right. So do you know the original definition of a meter?
No.
Okay, so somebody had to come up with that, right?
Right.
I mean, it's pretty obvious. A foot is somebody's foot, right? In the imperial units, but a meter was 1/10,000,000th the distance from the North Pole to the equator on a path that went through the Paris Observatory. So that's how it began, and that they became standardized. Then they created an artifact out of platinum and iridium, an alloy of those two, and that there was an etch mark on one end and on the other, and that was the length of the meter that you can go and reference it in France, so that you can then take a meter home with you that was the correct length. So that's an example. And they had an object called the kilogram, and it's in a vault, and there it is, 1 kg. All right, but point is, it had a beginning, and all of its metric beginning was in 1789. I'm just saying. Okay. So here we are in the United States, and we kind of have metric envy, a combination of metric envy and imperial pride. All right, we're using Fahrenheit and inches and meters and cups and tablespoons, and we're damn proud of it. But at the end of the day, I think it's like, yeah, maybe we kind of want a little bit of metric in our lives. So I just want to impress upon you, we already do. Are you ready?
I am ready.
And by the way, I'm saying we have been inching towards the metric system for decades.
I see what you did there.
Okay, so first of all, we had metric money from the start.
Okay, this sounds like Bitcoin. I'm not sure if I'm in.
How many pennies in a dime? How many dimes in a dollar?
Yeah,
all right.
It's base 10, yeah.
It's base 10 all the way. At the time, England was using pounds and shillings and pence and that. And I still don't know how that system worked. To this day, and I'm a full-grown adult who've thought about it, okay? So first we had metric money. Put that in the bank, okay? All right. What else do we have? Oh, our photography has largely been metric from the beginning, all right? There's 35 millimeter film.
Right.
You didn't measure that in inches, right? You had a 50 millimeter lens.
All lenses are measured in
All
millimeters.
lenses are measured in millimeters. Now, there was some film formats that were inches. There was 4x5 and 8x10. Those are the larger formats, but most of all the others was metric. And the lenses were metric. You go to the movies, 70 millimeter wide, 2001 A Space Odyssey, 1968, in 70 millimeters. No one was freaking out that you saw next to the 70.
Right.
Okay? Okay. So photography was in. All right. What else was in? Oh, our medicine has been metric, like practically forever. All right, so you have, it's 1 cc of some drug, or what is a cc? It's a cubic centimeter. That's what a cc is.
No doctor gives you a shot of an ounce of penicillin. I need an ounce of penicillin stat. Doctor, you're going to kill him. He's dead, Jim.
He's already dead, Jim.
He's already dead.
So medical dosing has been metric, like, forever. Okay. Add to that our nutrition labels. Those were metric from the beginning. How many grams of fat?
Oh, that's right.
How many milligrams? Okay. But just look on any nutrition label. It's all metric. And it's been that way. And no one is freaking out by looking at this. Okay? How many grams this? How many grams that? So, What do we have in the bank now? We got metric money, metric medicine, metric photography, metric nutrition labels. What else? Oh, we've got metric bottles of soft drink. You've never in your life purchased a quart of Pepsi. It's a liter.
Yeah,
no, you haven't. It's a liter. Right. Okay. A liter slightly more than a quart, but close enough, for most purposes. But, so 1 liter, 2 liter, 3 liter bottles of Pepsi.
That's right.
Okay. Yeah. So our larger volumes, non-dairy, larger bottles have been metric for a long time. Okay, for decades.
It's funny because everything you're mentioning right now are all global commodities.
Yes.
Soda is global. Photography is global.
Good point. We're not shipping milk.
Yeah.
That's correct. That's correct.
Pharmaceuticals are global.
Good point.
It's all global stuff that you're talking about.
Well, let me keep going. All right.
Okay.
I'm not done yet. One of the last things I thought would have changed was the volume displacement of the pistons in an engine. Okay. I drove a car that was a 400 cubic inch V8 engine.
That's right.
Nobody measures it in cubic inches anymore.
Not anymore.
It's in liters. That's right. 1 liter, 2 liter, and that liter, if you ever wondered, is not the volume of any liquid in it. It's the volume of the cylinders in the engine block itself.
4.0 liter. Yeah, that's right.
It's a measure of how much sort of movement and power you're getting out of the engine. It's one of several measures you can invoke. So that's metric. Okay. And shall I keep going? But those are important things, I think. Okay. Now we still have Fahrenheit, yes, and we still have sort of miles, and our cooking is not really metric. So there's like 3 holdouts: cooking, distance, cooking measurements, distance, temperature, and baking. Okay?
Right.
So when people say, America, you got to join us with the rest of the world with the metric system, we kind of already have. A. B, I don't feel, even as a scientist speaking, I don't feel some great urge to give up Fahrenheit and feet and inches. I'll tell you why. When you visit another country, part of what it is to sort of blend in and to fit in and to learn is to learn what their customs are. In America, Jack, we use Fahrenheit and just deal with it.
That's
okay?
Right.
I mean,
I'm not going over to my neighbors and trying to borrow 236 milliliters of sugar. Hi, I'm new to the neighborhood. Do you have 236 milliliters of sugar?
Slam the door back in their face.
Exactly.
So anyway, I think we come a long way. So we're inching, and maybe dairy comes next. I don't know. I kind of like the fact that eggs come in a dozen. A dozen is a nice historical baker's quantity.
I like that. Yes.
And so I'm cool with that. Let me remind you that we had a mission to Mars where the engineers were using the imperial system and the scientists were using the metric system. And there was a point where 2 calculations had to come together and their units were not converted to match. And so the propulsion that was put into play to go into orbit around Mars was the wrong thrust. And it basically overshot Mars completely. And so we lost, $100 million spacecraft because 2 systems didn't match. It's not because we weren't on metric. It's that because the system was not turned into a common set of measures. That's why. Had that been done, we wouldn't have had the problem, even if the engineers continued to use feet and inches. So,
wow. That right, well, okay.
That was egg on our face. That looked bad, especially for NASA.
Without a doubt.
Yeah,
You know what I mean?
Yeah.
It's like, missed by that much.
Almost. It doesn't count.
Yeah,
if you're trying to reach a planet, no, it doesn't count.
Damn. Oh.
Yeah.
That's awful.
Yeah. All right. So I just wanted to say we're inching towards the metric system, and we're there in ways you probably hadn't thought about. And so that's my little bit of that.
Yes.
And we're going to take a break. And when we come back, I'm going to talk about the difference between speed and acceleration.
Right on.
When StarTalk returns. We're back. StarTalk. This is a Stuff You Thought You Knew edition. I think it's our 2nd installment. Chuck, we did this once before.
Yes.
And I think you like it.
I do. It's now called Stuff I Still Don't Know. Still don't know this stuff.
All right. So for this middle segment, I want to talk about the difference between speed and acceleration.
Okay.
All right. So there's a nice scene. Nice. There's a rememberable scene in the movie Top Gun, where they just came out of their planes and they're holding their helmet, and what does one of them say to the other as they high five each other?
I've got the need for speed.
Okay. I thought it was
Thanks.
I feel the need for speed, and I want to push back on that, if I may. Okay?
You want to push back on the need for speed?
Yes, I am.
Oh no.
Because I claim that their speed is almost irrelevant to what it is that's triggering their emotions.
Really?
Yeah. Because, for example, right now, at our latitude on Earth, the rotation of Earth is carrying us due east at 800 miles an hour. Are you saying, I feel the need for speed and this is great? No.
That may explain why I keep throwing up every time I stand up. It could be a reason why I vomit.
See, I'm about to say that what we think of as motion sickness is not motion sickness, it's acceleration sickness.
Okay,
so Earth is in orbit around the sun 18 miles per second. All of these speeds are way faster than anything they're doing in their airplane.
This is true.
So they're not really after speed.
Wow, 18 miles in a second.
In a second. 1 second.
From my house, I would overshoot the Bronx. I mean, I would overshoot Brooklyn from where I am right now.
You'd end up in Long Island Sound.
I would. Oh, wow.
Okay.
In 1 second.
Okay. So you live in Jersey. You cross the Hudson River, the width of Manhattan, all of Brooklyn, and then you come out the other side.
Water. Oh, my God. That's amazing.
So here's the thing. When you are moving at constant speed, your body has no idea you're moving at any speed at all.
Okay.
It's only when your speed changes that you get some sense of motion. And by definition, when your speed changes, it's an acceleration. Now, in physics, an acceleration can be positive or negative. In the English language, we have another word for when it's negative acceleration. It's just called what?
Deceleration.
Deceleration. Okay.
Right.
So I might say acceleration in my next few minutes. I mean increasing or decreasing. It doesn't matter.
Either positive or negative acceleration.
Okay. When that happens, you feel it, and that's what you're reacting to. All right. By the way, think of velocity. Okay. So a change in velocity is an acceleration, and a velocity has a direction.
Right.
But suppose you're banking a turn, your direction is constantly changing. Well, if velocity has to have one direction, now I'm changing the direction, that's also an acceleration. So here's my point. When you're in a moving object, no matter its speed, if the direction or the speed changes, you are accelerating. And when you feel an acceleration, your body is going to respond. If you accelerate forward, your body will be thrown backwards. If you decelerate quickly, your body goes forwards. If you bank a turn, you lean against the door or against the person next to you in the front seat. So that's how you know you're accelerating, because your body is responding in this way. So these folks said, I feel the need for speed. It's because they're doing barrel rolls in their plane and upside down and all the stuff they're doing. That's what they're feeling. But if they were going perfectly at Mach 1, 2, 3, 4, or 30, they wouldn't be saying, I feel the need for speed, because that's not anything they would notice. This has been the complaint about the Lexus car. When it first came out, the Lexus was a luxury car, and that ride was smooth. I read one commentary, and it said it's like sitting on your living room couch while you're driving your car.
That sounds lovely.
Okay. So nobody who feels the need for speed is buying a Lexus. They want a car that can bank turns and go from 0 to 60 in how many seconds you're talking about. That's an acceleration.
Yeah, but it doesn't sound good to say, I feel the need for acceleration. It's a celebration of acceleration. Now I just sound like Jesse Jackson. You know, that's what I'm saying.
Because my man rhymes anything that comes out of his mouth.
Celebration of acceleration. Keep hope alive.
Okay, so that's all I'm trying to tell you. So that's why they will give top speed when you're buying a car. They will give a top speed, but they will also give 0 to 60 or 0 to 50 in a certain amount of time. So that is the change in velocity over a certain amount of time. And so if you change velocity in less and less amount of time, your acceleration is higher and higher and higher. That's why they keep trying to drop the acceleration time. Then it's more head snapping. Now,
right? Yeah.
Now,
that's why everybody loves Tesla.
Oh, because it's high. It'd be true for any well-made electric car. Will have very high acceleration.
Yeah.
Even at low speeds, right? Teslas can accelerate 0 to 60 in 3-4 seconds. Right?
Yeah, it's crazy.
Yeah, and I've been in it, and you can feel it. It's like,
yeah.
Okay. So now watch. Let's kick it up a notch. You ready? I don't think you're ready. Are you seated?
Okay. All right. I'm seated.
Okay.
Hold on, because I don't want to accelerate too fast. I better strap in.
Okay. So if acceleration is the rate of change of your velocity, okay, so if your rate changes quickly, you have high acceleration, you will feel this response all the more. Okay. All right. If acceleration is the rate and change in your velocity, what happens when you have a rate of change of your acceleration?
Oh my goodness. Let me guess. Your head explodes.
Yes, well, okay. So if you have a rate of change of acceleration, that has a term in physics. It's called the jerk. Okay? All right, so watch.
Oh, man, okay. That's great.
Okay, so watch what happens. You ready?
Go ahead.
I'm headed towards a brick wall. I'm trying to come up with these examples on the spot. Headed towards a brick wall. And so I should put on my brakes. So you put on your brakes, okay? And while you put on your brakes, you feel yourself, you're leaning into the shoulder strap, okay? When you hit the wall, your body jerks forward because you had a steady slowing down of your speed until your speed went to 0 instantly. So that is a rate of change of your acceleration, and then you feel a jerk.
Okay, but why did we run into a wall?
Okay, so the jerk is what actually does sort of musculoskeletal damage in an accident.
Oh, okay.
Okay, because we can sustain an acceleration, but when they say I have 1G, 2G, those are pure constant accelerations. But if you go from 1G to 6Gs in an instant, your whole body snaps.
Right.
That's this, and so the jerk is what
in reverse.
And the same thing in reverse, correct.
Gotcha. So what you're basically saying is jumping out of a 20-story window doesn't kill you.
That's correct.
It's the ground that does that. It's the ground.
If there were no ground, right, you'd be fine.
You're fine. Oh man.
So that's velocity, acceleration, and jerk. So almost every, and there's some cars they say, in this car you can feel the road. If you ever test drive like a sports car, they tell you that, right? Well, what does it mean to feel the road? Well, if the road were perfectly smooth, you wouldn't feel anything. So the fact that the road has certain bumps, the Lexus wouldn't feel those bumps because the tires are adjusting to it. But your sports car, which has, quote, rigid suspension, it is rigid enough so that you're feeling that, all right? So you and the road and the bumps and wiggles and the turns and twists on the road, you're feeling it all.
Nice.
You feeling it. And so this is what you like. This is what you seek. This is what the sports enthusiast is actually after, even if they're not self-conscious of it. Because if they only wanted high speeds, you can just get on a high-speed train, and then you don't feel it because they're smooth. No, you want to bank the turns and feel it.
That reminds me of a guy I was on the turnpike, and a guy comes by on a motorcycle, and I'm doing 80, so he had to be doing a little faster than 80 because he came by me. And then he pulls back on the throttle and pops a wheelie at 80 miles an hour.
Whoa.
And pulls off.
Okay.
So, and I'm pretty sure he was like, I feel the need for acceleration.
And with the high accelerating cars, of course, a constant acceleration is a one-time thing. By the way, you either press yourself back or forward or lean one way or another, and any abrupt change in that creates this jolt. But even if you're going at zero and then you floor it, there is the initial head snap. Okay, that's a very high moment of acceleration, but then you stays that way until you like hit the brick wall and then you snap in another way. So anyhow, I'm just putting all this out there in case you didn't know.
So all I can say is, please take Neil's word for everything he just said. Let's not try the brick wall experiment for ourselves. Okay? We're not responsible for anybody who crashes their car into a wall. All right? Just take his word for it.
Chuck, one last thing.
Okay.
All right. So if you're in an airplane and the airplane wants to just go left, let's say.
Right.
In the
First
old
it puts
days,
on its blinker.
roll down the window, put the hand out.
The pilot puts his hand out.
All right. So in the old days, the plane would turn and you would feel yourself lean one direction or another, depending on which direction it was turning. And if you had sort of a drink in your glass, you would see the level of the liquid tip inside the glass.
Right.
That doesn't happen anymore.
What?
Yep. It doesn't happen anymore.
Now,
Because
why wouldn't that
computers fly airplanes. The pilot's there just for show. All right? Computers fly airplanes. And here's what it does. When you're just sitting there doing nothing on an airplane going nowhere, gravity points straight down into your chair. You have a glass of water. Gravity points vertically down so the water level is horizontal. Okay. Now the plane takes off. While it's gaining speed, you press back. You'll see the liquid. Well, you're not being served liquid at this point, but it would actually change what it thinks is horizontal while you're accelerating. All right. So now you get up to 30,000 feet. You're going 500 miles an hour. That's speed, way faster than any car anybody's driving today. So there it is, and everything is level and horizontal once again. So now watch what happens. If, while the plane makes a left turn, depending on its speed, it can angle the fuselage so that your urge to lean to the right, in that case, is compensated by the banking of the plane itself. And the computer does it perfectly. So if you have a drink and you're sitting there, the plane can make a complete circle and you will never notice it because the combination of all the vectors line up in that computed trajectory of the plane so that everything goes straight into the bottom of the plane and into the chair. Even though everybody's actually tipped to the side, the fact that it's on a banked turn compensates for that, and so your drink is always horizontal. That's why no one even, if your blinds are closed, you'll never even know you were turning. Next time you come into the airport, do this experiment. Get your drink, put it there, notice its level, open the shade, look out the window, and watch the plane turn to come in for a landing, and as it does it, the water level is completely horizontal in your glass.
That's cool. The only problem, though, is the computer can't talk to you in that disaffected, I'm bored out of my mind, comforting pilot voice. Like, ladies and gentlemen, we're on our final descent to JFK. Just want to let you know that we know you have other choices to fly, and we thank you for flying with us. If you look out the left side of your plane, don't do that. You should look at the water in your glass right now.
Exactly. Do some science while you do it. All right. So when we come back, I've got another segment here of stuff you thought you knew. So, Chuck, you want another one of these?
I want another one. Any hints on what it might be?
Oh, yeah. It's just on heat shields.
Oh, sweet.
Let's do it.
All right.
Okay. All right. When StarTalk returns. We're back. StarTalk. Chuck Nice tweeting at Chuck Nice Comic. Dude.
Thank you, sir. Yes.
You had some good stuff lately. Keep it going.
Thank you.
All right.
Yes.
All right. So I want to talk about heat shields on aircraft. Okay. So we all know that they exist. And do you know why they exist?
To stop phasers from penetrating the ship's hull?
I didn't say. That's a different kind of shield. Oh, my heat shields.
Damn.
Not phaser shields.
Oh, man.
Damn. Oh, you don't want to hang around anymore. Okay. Ordinary heat shields. Okay. You've always seen, you've heard about it, you've read about it. And do you know what they're for?
I would guess because it gets hot. So they're going to shield you from the heat.
Okay, that's not their purpose.
What?
Yeah, that's not why they exist.
Well, that's a very deceptive name then.
Yes, it is. I thought about that. That's right.
Yeah, that's an extremely deceptive name.
It implies that you're going to get hot and burn up, so you have to protect yourself from it, and so you put in these shields so that you don't die.
So why is NASA toying with my emotions like this?
Cause now you care, because the astronauts is living fleshy things inside the capsule.
Right.
Okay.
So if it's not to stop me from burning up and dying, what's it for?
Okay. So here it is. You ready? You need heat shields because any object in orbit is going, especially low Earth orbit, is going 18,000 miles an hour.
Right.
Okay?
That's right.
That's fast. So if you do the math, that's like 5 miles per second.
Second. Yeah.
8 kilometers a second. All right? So that's fast. Well, if you're going that fast in any other situation, you'd put on the brakes, right? You would find some way to slow down. Well, spacecraft don't also carry fuel to slow down with.
No retro rockets.
No retro rockets.
Now they do.
Well, no, not really. No. Well, it depends. Wait, no, hold on. When they're coming back to Earth, no retro rockets. Okay?
Still no retro rockets.
Still no retro rockets. So, but you're right. It would be called retro rockets. So I'm going so fast. Let me flip the engine the other way or point the nozzle and blow exhaust opposite the direction I'm going. That will slow me down. Okay? If we had that, that's all you'd have to do to come out of orbit is blow exhaust out the other direction until you have zero velocity, pop a parachute, and then glide down to Earth.
Yeah, like in a ship, like all engines reverse, and you see the propeller stop and go the opposite direction.
Correct. Okay, that's all you'd have to do. But to carry the fuel that you're not going to use until you want to come out of orbit, that takes fuel to put the fuel that you're not burning. And so we said, we're not going to do this because we don't have to. Let's take all of this kinetic energy, this energy of motion, and let the atmosphere burn it off. Let the atmosphere sweep it away. So they're called heat shields, but you know what they are? They're aerobraking. It's an aerobraking system.
Uh-huh.
You want this because you intentionally didn't bring fuel or brakes to slow you down. So you use air to do it. So what do? Here's the capsule in orbit, moving real fast, okay? And it's set up in such a way that the bottom section, it'll always sort of dangle with that coming first. And it's this big blunt thing that plows into the atmosphere. The atmosphere is, I'm not going to want to let you do that, but I'm coming through anyway.
Yeah, it's not aerodynamic at all.
It's totally not, it's aerodynamic in that it's not going to be turbulent. It'll stably come through, but you want to maximize this resistance. And in so doing, you heat up the bottom side of the craft. Where does the energy come from that's heating the bottom of the craft?
The air friction.
I know, but okay, what was the original source of that energy?
What do you mean?
It was your speed of the craft.
Oh, that's right. The craft itself flying in at 18,000 miles an hour.
Thank you. We got to get rid of that energy somehow. So here it comes. All right, let us come down and work our way into the atmosphere. And in the upper layers, there's not as much air molecules, but there it is. And you get sort of shock waves and friction and all manner of other sort of communicating molecules. All right. And that speed becomes heat energy. The kinetic energy becomes heat energy. Now, if it only becomes heat energy, that's not good enough because then you'll still burn up. You've got to whisk away that heat energy somehow.
Right.
Okay? Send it somewhere else. Get it out of here. So in the old days, and even in many modern capsules, the, quote, heat shields are onion layers of burnable substance.
Oh, so they are heating up and then they're peeling away. So all the heat is actually like wicking, like moisture wicking.
I like that analogy. You're wicking away the heat. And every time you do this, the thing is slowing down and continues to slow down. And depending on how much kinetic energy you have, add on a few more layers. Okay? When they came back from the moon, they re-entered the atmosphere at a higher speed than just coming out of low Earth orbit. So the moon crafts coming back had more heat shield layers than the other spacecraft.
Wow. That's, by the way,
it's aerobraking. That's what it is.
Ingenious.
It is, and it's blunt, and it's low tech, and it worked every time.
I don't know who thought of that, but that guy should have got a donut. I'm telling you, or a parking space.
The reward?
He should have got something. He should have got a parking space because that is.
Says the New Yorker, where parking space is highly valuable.
Somebody was really thinking. I mean,
yeah, and it works, and it works every time. So it's. I think the correct word is it ablates. Ablates. You're saying whisking, it ablates. And it goes away. And when you're done and you have low enough speed, then you deploy your parachute and you just dip in.
That is genius.
There is a sci-fi movie where they are in orbit around some planet. I think it might be Mars, but it's some planet. I don't remember which. And they're on some stable orbiting platform. But there's one of these platforms that sort of rotates with the rotating planet. Okay, and a guy falls off the platform towards the planet. And that's bad. And then he goes down, and then you see him disappear in a puff of smoke. No. Just because you're entering an atmosphere doesn't mean you're going to burn up.
Right.
The burning up is not an inherent feature of passing through an atmosphere. The burning up comes from getting rid of the speed you had to maintain 18,000 miles an hour. When we landed on the moon's got no atmosphere.
Right.
How do you get a soft landing there? Can't use a parachute. Can't use aerobraking. They needed retro rockets.
Got to have retro rockets.
Yeah.
Yep.
There it is. Mars has a thin atmosphere, so that one had big parachute, plus retro rockets, plus aerobraking. All three to get the rovers on Mars.
Or you drop a trampoline.
Thank you. Well, I'll bring that up at the next NASA meeting, okay?
Chuck Nice says, trampoline. Why did it take us 5 days to land on the moon?
Yeah, if it's a perfect trampoline, it will never stop. It'll never dissipate the energy. It'll just keep bouncing. But you want it to, the energy has to dissipate somehow. It'll heat up the springs. The energy can't just disappear. It has to transmute into some other form and then get whisked away, as you said. So I think you should always think of heat shields as aerobraking systems rather than, you need this, otherwise you'll burn up. No, you need it, otherwise you'll crash.
That's so cool.
And
that's really cool.
Oh, and in the movie 2010, ostensibly the sequel to 2001, they came to Jupiter and they aerobraked around Jupiter. They had some really good visual effects for the day. And they're inside the craft, they're saying, oh, wow, this is, I wish I could see this from the outside, this aerobraking. Basically, any spacecraft with heat shields coming through an atmosphere is aerobraking. Anytime. So that was not some new thing. It was portrayed as some new innovative concept But of course, we do that all the time. In fact, there are spacecraft that come into Mars and their orbit is highly elongated. That's a higher energy orbit, and they want to sort of circularize it. So when it dips down closer to the atmosphere, it makes sure that the atmosphere slows it down a little bit. That eats some of the energy, and you can circularize an orbit on purpose that way.
So they just kind of like skipping rocks.
Skipping rocks. I like that.
That's cool.
So there you go, Chuck. Think of it as aerobraking, not heat shields for the future.
Very nice. Do not try this on Earth. That's all I can say. Please don't try this on Earth. But that is a really cool concept.
And if you fall out of your spaceship and fall towards a planet,
Right.
If you die, it won't have to be because you burned up.
Right. It'll just be because you hit the planet.
Hit the planet.
Right. Either way, that dude was going to die. So
this was yet another episode of stuff we thought you should know, whether or not you did. All right, Jack, my co-host.
always a pleasure.
All right, Neil deGrasse Tyson, as always, keep looking up.